Got another exam walkthrough from Capacitence. This is going to be 2024 October, question 14. Again, like usual, you can solve the question and then watch me solve it. For the MS and the ER examiner report, you can go to the end of the video. So it says the diagram shows a circuit with the cell of potential difference V0 in series with capacitor, resistor, and switch. And we have a voltmeter which measures the potential difference across the capacitor, and then it says the capacitor is initially uncharged, and then you close the switch and the capacitor charges. Basically, this is a charging circuit that we have got here, and then we've got a charging graph there that we get, and then we get to the question which says explain the variation of V with time as shown in the graph. You should refer to the charge on the capacitor and the current in the circuit. So first of all, you know that you have to talk about the charge on the capacitor, and you also have to talk about the current in the circuit. So remember to mention these 2 points in your answer. And next, the main thing we have to mention is we have to explain the variation of V with time. Okay, so these couple of things, keep them in mind, okay, because they've kind of already helped you out by telling you some things. And yeah, now I'll explain a little bit of the background of this question, and so you can understand the question, and when I write the answer also, you don't have any doubts. So let's go through that, and then I'm going to write the answer. Okay, so what we're going to be looking at now is we're going to be looking at this circuit. It's the same thing. We have an ammeter, capacitor, resistor, and a battery. A positive here and negative here. Switch is currently open, and the capacitor is currently fully discharged. And there are equal number of positive and negative charges on the capacitor. We have equal number of the electrons and holes. Now what are holes? Is basically just empty spaces that kind of act like positive charges. And they're basically empty spaces which the negative charges can come in and take place of. Okay, so we have the capacitor. It has potential difference of 0 right now. On each plate, the charge is going to be 0. So that's what's going on. Now what's going to be happening is that we're going to be closing the switch and the electrons are going to start to move. So let's talk a little bit about electrons. So the electrons, this is the negative side, are going to be flowing from here through the resistor to the capacitor. And they're going to be filling in those empty spaces, the electrons. So they're going to be filling those spaces in, and there's going to be less space or less of those positive particles or holes, as the right word there would be. And then what's going to be happening on the other plate is that electrons will be moving out of this plate and going towards the positive side of the battery. And we can see that there is going to be a negative charge developing here and a positive charge developing here. The main point is that the charge is increasing. Okay, now I'm going to pause here and we're going to talk about potential difference now. Now I hope you remember your Kirchhoff's voltage law, which said that the sum of EMF is equals to the sum of the potential difference. Now for this we can say the potential difference, we can say the EMF of the battery first is going to be equals to the potential difference across the capacitor plus the potential difference across the resistor. Okay, so that's what the equation looks like. Now the potential difference across the capacitor is going to be increasing, and the potential difference across the resistor will initially be maximum but will be decreasing. Okay, and the reason for this is because the charge on the capacitor is increasing, and because of that the potential difference across the capacitor is going to be increasing as well. And on the other hand, the potential difference across the resistor will be decreasing, and it will be getting less of the proportion of the EMF. So that's what's going to be going on. And the current, because of this, is going to initially be at max, and then it's going to decrease to 0. Now when the capacitor becomes fully charged, we can see that this plate and this plate, they both have a lot of negative and positive charges. Now what's going to be happening is these negative electrons, they're not going to be moving anymore because they're repelled by these electrons here. You can connect it to your electric field chapter where we talk about there's going to be electric force, and we can connect it to that as well. And then we have the holes here, or we can assume them or take them to be as positive particles, and we can see that there's positive here and there's positive here, and so the electrons are are kind of not moving because they're attracted at this side and they're attracted to the other side as well. So what we can basically say is that the electrons are going to stop moving eventually, and so the current will become zero, because the current is the rate of the flow of the charges, and if the charge is not flowing, the current is zero. Okay, and you can see here a bit closer the same thing again. Okay, so I hope this kind of clears up the things that we're going to be discussing when we answer that question. I'm going to show you a quick animation, and then we're going to answer the question. Okay, so your answer is going to look something like this. When the switch is closed, there is a current. Okay, so there's a current in the circuit, and the charge on the capacitor increases because of this. And then the PD across the capacitor increases, the PD across the resistor is going to decrease, as the current is also going to decrease in the circuit from a maximum to a zero. And then the PD across the capacitor increases at a decreasing rate. I'm going to talk more about this in a bit. And then when the PD across the capacitor is equals to the EMF of the battery, the current, this is not 1, it's the current I is equal to 0, and the capacitor is fully charged, and the PD across the capacitor remains the same. This last point here is basically talking about the graph, what you're going to be seeing on the graph. Okay, so it becomes constant, and then it's going to increase at a decreasing rate. So these are the two types of graphs I'm going to draw that you'll come across in your capacitance chapter. So you'll have the discharge graph of current, charge, and the potential difference across the capacitor, and the charging graph of the current. They all have the same shape. And then you have the charging graph of current and the potential difference across the capacitor. So these graphs kind of look like this, and then they decrease to 0, and for this graph they increase and then become constant at a specific value. Let's call it x naught. Okay, now the way you describe these graphs is that this type of graph we can say is increasing at decreasing rate. It's going to be increasing at decreasing rate. Okay, so increasing at decreasing rate and decreasing at decreasing rate. Okay, so that's how we describe these graphs. I'm sure you're familiar with this. We studied this in the kinematics chapter as well.